Financial Planning and Control, the Operational Break-Even Point Analysis.
Hi! This video class presents the Operational Break-Even Point concept. To start, keep on hand one HP 12C financial calculator, pencil or pen, and white paper to take notes. To follow this class, you need to have previous knowledge regarding costs accounting, understand fixed and variable costs, and to be familiar with the income statement.
Part 1 of 4. The Operational Break-Even Point Concept in Units.
The break-even point analysis, sometimes called cost volume profit analysis, is used by organizations to determine the operational level required to cover all operational costs and to evaluate the profitability associated to several sales levels. Before proceeding, I will show you the algebraic notation to be employed during this class. Note this down. P equals unitary sale price in monetary units. V equals unitary operational variable cost in monetary units. F equals total operational fixed cost in monetary units. And Q equals quantity of sold units in products or services. Concept. The operational break-even point of an organization in units is the sales level required to cover the total operational cost of the company, that is, the sum of its fixed costs and total variable costs. In the break-even point, the earnings before interest and taxes, or EBIT, are equal to 0. The first step to identifying the operational break-even point is to separate the cost of sold goods and operational expenses into operational costs fixed and variable. The fixed costs are a time function and are independent of the sales level, typically being contractual. The variable costs vary according to the sales level and are a volume function and not a time function. To assist you in fully comprehending the operational break-even point in units, I will present in the next part two complementary approaches, the algebraic and the graphic. Let's go ahead.
Part 2 of 4. Algebraic approach to the operational break-even point in units. Analyze the simplified operational structure of the income statement on screen. Sales revenue, a result of the quantity in units of products or services sold Q, multiplied per the unitary sale price P, minus the total fixed operational cost F, minus the total variable operational cost as a result of the quantity in units of products or services sold Q, multiplied per the unitary variable cost V. We can see, as a result, the earnings before interest and taxes, or EBIT, also called operational result. Based on this column, we can construct an equation to calculate the EBIT. Here it is. This equation can be simplified. Take a look. As I showed you a few minutes ago, we already know at the operational break-even point, the operational result, or EBIT, is equal to 0. Substituting the EBIT for 0 in this equation, and by reordering the terms to isolate Q, it's now possible to write the equation which defines and allows us to calculate the operational break-even point in units of goods or services sold. Pay attention to this. We will now analyze an illustrative numeric example. Take a little break in the video and copy this equation of the operational break-even point in units. One company sells its only product for 10 per unit. Each produced unit has a unitary variable cost of 5. The total operational fixed cost is 2,500. Using these values, calculate the operational break-even point in units for this organization. Applying this equation and substituting these values, we can calculate the operational break-even point for 500 units, as you can see. Let me ask you, are you sure that 500 units is in fact the break-even point? Will selling 500 units generate sufficient revenue to cover all costs, result in an EBIT equal to 0? Let's confirm this. 500 units, each one sold at 10, generates 5,000 in sales revenue, minus 2,500 of operational fixed cost, minus 2,500 of total operational variable cost, resulting from 500 units multiplied by 5 of unitary operational variable cost. And the result, as was expected, is an EBIT equal to 0, demonstrating that this equation is correct, at the same time numerically illustrating the concept of the operational break-even point in units. Next, I'll show you the graphic approach to the operational break-even point analysis. Take a little break in this video to drink some water. Part 3 of 4. Graphic approach to the operational break-even point in units. Observe on the screen this Cartesian orthogonal coordinate system. On the x-axis are the sales in units. On the y-axis are the monetary variables, that is, revenue from sales and costs. This axis is in 1000 scale. The graph will be built using the same numerical example previously shown, where the unitary sale price was 10, the unitary operational variable cost was 5, and the total operational fixed cost was 2,500. Remember, the calculated operational break-even point was 500 units. In this graph, I draw 4 straight lines: total revenue, total fixed cost, total variable cost, and total cost. Each straight line will be drawn using 2 points plotted over the coordinate system. Next, the break-even point and the areas corresponding to positive and negative EBIT will be highlighted. All this information is crucial to perfectly characterize this graphic approach. Let's start with the operational fixed cost straight line. If we sell 1000 units, the operational fixed cost is 2,500. If we sell 500 units, the operational fixed cost obviously remains at the same value, 2,500. Having the 2 points plotted on the coordinate system, we can draw the straight line. Pay attention, the chosen points 1000 and 500 units are arbitrary. If we had used, for instance, 800 and 200 units, the generated straight line would be exactly the same. Now, let's draw the total operational variable cost straight line. If we sell 1000 units, the total operational variable cost will be 5000. If we sell nothing, the total operational variable cost will be 0, that is, the total operational variable cost straight line cross the graphic origin. I warn you again, the chosen points 1000 and 0 units are arbitrary. If we had used other quantities, the generated straight line would be exactly the same. This characteristic is valid for all straight lines which will be drawn in this approach. I advise you to try several values to confirm what I'm telling you. Let's draw then the total operational cost straight line, that is, the sum of the total operational fixed cost and the total operational variable cost. If we sell 0 units, what is the total operational cost? In this case, it is 2,500 of total operational fixed cost plus 0 of total operational variable cost. Consequently, for 0 units, the total operational cost is 2,500. This is our first point. And if we sell 1000 units, how much will the total operational cost be? In this case, it is 2,500 of total operational fixed cost plus 5,000 of total operational variable cost. Therefore, for 1000 units, the total operational cost is 7,500. This is our second point and the total operational cost straight line. To finalize, let's draw the revenue straight line. If we sell 1000 units, the revenue will be 10,000. But if we sell nothing, how much will the revenue from sales be? 0, of course. By connecting the points, the total revenue straight line appears. This straight line, like the total operational variable cost straight line, for the same reason also crosses the origin of the coordinate system. Observe then a curious thing. The total revenue straight line intercepts the total operational cost straight line at exactly 500 units, the operational break-even point. This point, plotted on the graph, is a kind of milestone. If we sell exactly 500 units, as I previously showed you, the EBIT will be 0. Above 500 units, the operational result, or EBIT, is positive. This is the positive area of the EBIT highlighted on the graph. Below 500 units, the operational result, or EBIT, is negative. This is the negative area of the EBIT, also highlighted on the graph. That's it, the operational break-even point graph is ready. A constructive recommendation is to stop this video and appreciate this structure a little bit more. To improve your reflection, I will ask you 3 questions based on the numbers from this example. Firstly, keeping all variables constant, what will happen to the operational break-even point if the total operational fixed cost rises? Will it rise or fall? Secondly, keeping all variables constant, what will happen to the operational break-even point if the unitary operational variable cost rises? Will it rise or fall? And thirdly, keeping all variables constant, what will happen to the operational break-even point if the unitary sale price rises? Will it rise or fall? I will review the answers in 10 seconds. Think about it. Part 4 of 4. What happens to the operational break-even point if? This is the basic situation, our numerical example, where the operational break-even point calculated is 500 units. If, in comparison with the basic situation, the total operational fixed cost rises, for example, to 3000, the operational break-even point will rise to 600 units. Hence, an increase in the operational fixed cost generates an increase in the operational break-even point. If, in comparison with the base situation, the unitary operational variable cost rises from 5 to 7.5, the operational break-even point will rise to 1000 units. Therefore, an increase in the unitary operational variable cost causes an increase in the operational break-even point. If, in comparison with the base situation, the unitary sale price rises from 10 to 15, the operational break-even point will fall to 250 units. So, an increase in the unitary sale price causes a decrease in the operational break-even point. Please observe the box on screen. It summarizes this part and concludes this theme. This video class is finished. Thanks for watching.